Good morning, everyone. Today we are presenting our project titled Beyond Transcription, End-to-End Aphasia Phenotyping using Multimodal Large Audio Language Models. And this is for the team Batch 10, which is Arnama Muralidharan, Jalak Vashishta, and Michelle Sarah David. And this project comes under the domain of machine learning, and it focuses on developing an explainable multimodal AI system for automated aphasia diagnosis using raw speech under the guidance of Ms. R.K. Kapalavani. Aphasia is a neurological language disorder commonly caused by stroke and brain injury. It affects a person's ability to speak and understand language. Millions of people globally are affected by aphasia, and delayed outcomes often lead to poor treatment outcomes and long term social isolation. Current systems rely heavily on manual clinical assessment and transcript based speech analysis. This problem with transcript only analysis is that it completely ignores critical acoustic biomarkers present in raw speech signals itself. Features such as hesitation, speech pauses, articulation, slurred pronunciation, and prosodic variation are lost during transcription. These features are extremely important for differentiating aphasia subtypes such as Broca's aphasia and Wernicke's aphasia. Another major limitation is that most automated diagnostic systems behave like black boxes. They provide a prediction, but often fail to explain the reasoning behind that prediction, which significantly reduces clinical trust and adoption. Additionally, there are shortages of trained speech therapists and neurologists, especially in rural and underserved regions. This leads to delays in diagnosis and treatment. To address these problems, our project proposes an end to end multimodal framework that directly processes raw speech audios instead of relying only on text transcripts. Traditional systems convert speech into text and then perform NLP based analysis. However, this process discards valuable information that lives directly inside the waveform. Our project instead uses an end to end multimodal framework that directly processes raw audio signals. We use a Qwen 2 Audio 7B large audio language model, which allows the system to jointly learn linguistic and acoustic representations from patient speech. Unlike traditional pipelines that first convert audio into text, our system directly listens to the waveform. This enables the model to capture hidden acoustic struggle behaviors such as reduced fluency, abnormal pauses, prosodic flatness, articulation difficulty, and more. These subtle speech patterns are extremely valuable for clinical phenotyping. Our objective is to implement a chain of thought reasoning framework so that the model does not simply produce a label, but also generates a clinical rationale explaining the reasoning behind the diagnosis. This improves transparency and clinician trust. Our second objective was early detection of aphasia subtypes in order to improve rehabilitation outcomes through faster intervention. The third objective is lightweight deployment. We want our systems to run on standard hardware without requiring expensive medical infrastructure or enterprise grade GPUs. Our work closely aligns with Sustainable Development Goals as well. It supports SDG 3 by improving healthcare accessibility, SDG 9 by advancing multimodal clinical AI systems, and SDG 10 by reducing inequalities in healthcare access for underserved populations. Now, there are three major issues that are associated with end to end audio based diagnosis systems. The first is noise sensitivity. Since a model directly processes raw audio, background noise, and recording, the quality can strongly affect the biomarker extraction. Another challenge is phenotypic overlap. Certain neurological disorders, such as aphasia and early stage dementia, can produce similar speech patterns, making classification difficult. Interpretability is also extremely important in healthcare AI. Even though a model generates clinical rationales, those rationales must align with established neurological standards, so the system should not hallucinate any symptoms or incorrectly classify normal speech pauses as pathological behavior. Another major challenge is multilingual generalization. Speech struggle behaviors can vary across different languages, cultures, and speaking styles. There's very limited clinically labeled audio data available for regional languages. The computational challenge was also significant because fine-tuning a 7 billion parameter model requires large GPU memory. To overcome this, we use 4-bit quantization along with a parameter-efficient fine-tuning technique known as LoRa to do this. Patient privacy and ethical compliance are also key concerns. Since we are working with clinical voice data, our preprocessing and inference pipeline is designed to avoid exposing personally identifiable information during model extraction. For our literature review, we analyzed several recent papers related to multimodal healthcare AI, aphasia detection, explainable language models, and clinical reasoning systems. One of the most important observations from the literature was that multimodal systems consistently outperform text-only approaches in neurological diagnosis tasks. We also found that chain of thought reasoning is significantly improving interpretability and diagnostic reliability. Another important finding was that acoustic and linguistic features together provide better diagnostic performance than either modality individually. Several studies also highlight the importance of explainable AI in healthcare systems, since clinicians require interpretable evidence before trusting automated predictions. These insights are directly influenced by our architecture design. The following slide shows a complete architecture of the proposed system. The workflow begins with an offline training using the Aphasia Bank's dataset and APROXA subsets. These datasets contain paired speech recordings and clinical transcript annotations. The front end allows clinicians or patients to upload speech recordings in WAV or MP3 formats through a Flask-based web application. The uploaded audio first passes through the preprocessing pipeline, and here the audio is V-sampled to 16 kHz. Silence regions are also trimmed, and the waveform is converted into tensors suitable for the modal. The processed input is then passed on to the fine-tuned inference engine. To make deployment a lot more feasible on limited hardware, the model uses 4-bit quantization. Finally, the system generates the diagnostic report, which includes the predicted aphasia subtype, confidence score, probability output, and the explainable clinical rationale. For implementation, our system requires an NVIDIA T4 or an L4 GPU with at least 16 gigabytes of VRAM because we are working with a 7 billion parameter audio language model. The primary frameworks used are PyTorch and Hugging Face transformers. We also use Unsloth for accelerated fine-tuning, PEFT for LoRa implementation, Bits and Bytes for quantization, and Librosa for audio preprocessing. Development is carried using Google Colab and Jupyter Notebook environments, along with Visual Studio Code as well. The project is predominantly divided into 4 major modules. The first module handles data preprocessing and base model initialization. The second module implements parameter-efficient fine-tuning using LoRa. The third module focuses on validation, evaluation metrics, and explainable AI analysis. The fourth module implements a front-end application interface for clinical deployment. The preprocessing pipeline begins by standardizing all audio recordings to 16 kHz monochannel formats. This ensures consistency across all training samples. Then, silence trimming is done to reduce noise, and this removes any unnecessary acoustic artifacts that could interfere with biomarker detection. These recordings are then segmented into 30-second chunks, and this segmentation strategy optimizes the context window of Qwen2's audio model and increases the number of usable training samples. The processed audio is then passed on to Qwen2's audio encoder, followed by 4-bit quantization, and then we use bits and bytes for memory optimization. The dataset used is Aphasia Bank, which provides paired speech recordings and transcript annotations. The recordings were segmented into smaller chunks to improve processing efficiency and maximize usable context within the transformer model. All audio inputs are normalized into 16 kHz mono format with silence trimming to reduce background noise, and the model's architecture directly aligns with acoustic embeddings with the language embedding space, allowing the model to jointly learn speech acoustics and linguistic information. To support deployment on standard GPUs, we implement 4-bit quantization, reducing VRAM usage significantly while preserving model performance. And finally, all these processed samples are converted to a JSON-L instruction fine-tuning format. The original dataset contains 40 aphasia recordings and 40 healthy recordings. Using segmentation augmentation, we expanded these recordings into approximately 2,400 audio segments suitable for LoRa fine-tuning. The dataset distribution consists of roughly 76% of aphasia samples and 24% of healthy control samples. The waveform and spectrogram visualization shown here demonstrate the acoustic differences between healthy and aphasic speech patterns. This slide shows the implementation snippets from the preprocessing pipeline. So essentially, the code handles audio loading using Librosa, sample rate normalization, chunk segmentation, and tensor preparation. The second section demonstrates quantized model loading using bits and bytes configuration for efficient GPU memory utilization. Module 2 focuses on PEFT using LoRa, which is low-ranked adaptation. Instead of retraining the entire 7 billion parameter model, we freeze the pre-trained back model and insert trainable LoRa adapters into transformer attention layers. And this significantly reduces computational overhead while preserving the pre-trained language understanding capabilities of the model. The training loop also uses gradient accumulation and optimized schedulers to stabilize fine-tuning on limited clinical data. And the optimization objective is used by cross-entropy loss. The main purpose of PEFT is to essentially bypass hardware limitations associated with full model fine-tuning. So instead of updating all model parameters, LoRa updates only lightweight adapter matrices while keeping the original backbone frozen. This dramatically reduces memory consumption and allows the model to fit within a 16 GB VRAM GPU environment. And this diagram illustrates how LoRa adapters inject low-rank trainable matrices into frozen transformer layers during backpropagation. The pre-trained weights remained fixed while the adaptive layers learn task-specific updates related to aphasia detection. This allows efficient learning without catastrophic forgetting. LoRa was applied specifically to attention modules such as query projection, value projection, key projection, and objective projection. These layers are responsible for attention computation within the transformer architecture. By fine-tuning these specific layers, the model learns aphasia-specific biomarkers while preserving the general language understanding. Only around 1% of the total parameters were updated during training. The LoRa configuration uses a rank value of 32 and an alpha value of 64. These settings help the model capture subtle acoustic struggle behavior such as dysarthria and prosthetic flatness. Training stability was improved by using gradient accumulation, and CE loss is used to minimize divergence between generated rationales and ground truth clinical labels. The fine-tuned model is then evaluated using a held-out test split from the aphasia bank dataset. We use a confusion matrix to visualize subtype misclassification patterns between aphasia categories. Rouge and blue scores were also used to evaluate the semantic quality of generated diagnostic reports against expert annotations. The validation results achieved at approximately 89% accuracy with strong precision and recall scores for aphasia detection. The confusion matrix demonstrates strong classification performance across aphasia and healthy control categories. The sample output shown here compares the generated prediction against the ground truth label. Explainability is a major focus of the system as well. We implement chain of thought prompting where the model is instructed to think before diagnosis and generate structured clinical reasoning. Second, we visualize transformer attention weights to identify which temporal regions of speech influence the prediction. Third, we implement SHAP analysis to measure the contribution of different acoustic and linguistic biomarkers. This slide shows the implementation snippets for rapid generation, attention visualization, SHAP integration, and clinical rationale generation. These components together improve interpretability and allow clinicians to validate model predictions more effectively. This slide shows an example of the final diagnostic report generated by the system. It includes a predicted aphasia subtype, confidence score, chain of thought clinical reasoning, and SHAP-based biomarker attribution. Instead of simply generating a label, the model explains the speech characteristics that influence the final diagnosis. The graph on the left shows the training and validation loss curves throughout optimization. The steady reduction in loss indicates stable convergence during fine-tuning. The SHAP feature importance graph on the right shows that fluency speech and frequency and syntactic complexity have the highest contribution towards diagnosis as well. And these graphs represent the rouge and blue evaluation metrics for generated clinical rationales. The scores demonstrate strong semantic overlap between the generated reports and expert medical annotations, indicating that the model produces clinically meaningful explanations. This table compares our proposed framework with existing baselines and shows how our model achieves approximately around 89% accuracy while also providing explainability through COT reasoning and SHAP attribution, while traditional systems achieve a lower accuracy and lacked explainability. The model was deployed using a Flask-based web application inference pipeline through a scalable backend API. Clinicians can securely upload patient recordings, and the dashboard predicts the confidence score and the generated clinical rationale. A waveform visualization is also integrated to verify the signal quality before diagnosis. So this shows a front-end upload workflow where you have a speech sample and the system pre-processes the audio, following which the system performs inference and we finally get the analysis progress. And the interface shows the final prediction results. The dashboard shows the predicted subtype, confidence score, feature importance analysis, and supporting acoustic biomarkers. And this slide demonstrates the temporal analysis module as well. And these are our references used throughout our project for architecture design, explainability techniques, multimodal healthcare AI, and aphasia detection methodologies. To conclude, our project introduces the end-to-end multimodal framework for aphasia phenotyping and large audio language models. Now we will move on to the demo section. So let's look